Ladies and gentlemen, our class recording for today has started. So, chapter 5 in your book deals with chemical bonding. Earlier in the year, we were introduced to this, right? The periodic table. And we talked about the periodic table shows us the different elements that exist out there in the real world. And back in the 1800s, Dalton puts forth his atomic theory, right? And he said that all atoms of the same element are identical. So all atoms of oxygen are exactly the same, but atoms of different elements are different. So oxygen atoms are different than nitrogen atoms, right? And for the most part, we believe that to be true. Isotopes throw a little wrinkle in that, but still, that's kind of the same thing. But if we look at our periodic table, this one that I've listed up here only goes up to 118. So there are 118 different kinds of atoms that exist out there in the universe. But if you look around this room, before we go there are 118 different kinds of atoms. And all those 118 atoms are different from the other 117, right? But if you look around this room, you could probably pick out more than 117 different kinds of things that exist in this room. This table is different from this piece of paper, right? This piece of paper is different than this remote control. This remote control is different than this bag, etc., 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 right? It's all different.
I was hoping you said baseball, but that was...
Baseball is different, but even on the baseball, Andrew, right? Like, the outside of the baseball is different than the stitches, and then the stitches are different than the writing, right? And so all these things are different. If we go around this room, we could probably pick out more than 118 different kinds of things. And that means that somehow, some way, these 118 things can come together to form more than 118 different kinds of substances, right? Does that make sense? That if there's more than 118 things out there in the universe, somehow these can join together to make different stuff. Maura, go ahead.
Is that like when you like you said to do the problems where it's like, how many different outfits can you make if you have like 6 shirts?
Yeah, right. Yeah, I mean, it's basically yes. That, if you have, like I said, if you have 6 shirts, 6 pants, and 6 different kinds of shoes, it's not only that you have 6 different outfits, right? You can mix and match and make different things. That's exactly kind of what we're talking about. That these elements are all different from one another, but we don't only have 118 outfits, right? There's lots of different outfits, okay? And so somehow they have to come together to make different stuff. And that leads us into chemical bonding. So, for this definition, chemical bonding. Chemical bonds are an attractive force that hold atoms together. An attractive force that holds atoms together. That attractive force that holds atoms together results in a new substance. And we will talk a little bit more about that in the next unit. Once we talk about what bonding is, we'll talk about how it happens a little bit more. Like so many other things in this class, and that's why we introduced this concept way, way early, bond formation is an energy process. And we've talked about that energy affects so many things that happen out there in the real world. And specifically, what are objects or substances trying to do with energy? How do they want to exist from an energy standpoint? High energy or low energy? Low energy, right? That's the reason why things happen is because objects generally want to get to a lower energy state, right? If I roll this ball off the table, right, start it rolling towards the edge of the table, once it gets to the edge of the table, what happens? It falls. Why? How much energy does it have on the floor versus up here on the table? Less energy, That's why it falls, right? That's why things happen. We're generally trying to get to a lower energy state, and that's why things bond with each other, right? So, bonds will form if atoms have a lower energy together than they did when they were separate. So bonds will form if they have a lower energy, if atoms have a lower energy together than they did when they were separated from one another. We generally, sorry, boring.
Why are you laughing at me?
We generally say that bond formation is an exothermic process. And that means that the products of a reaction have less energy than the substances that you started with. Right? Things tend to get to a lower energy state. So what you end up with has less energy than what you started with. Now, because you know English, you probably can figure out a little bit about exothermic, right?
Outside heat.
Outside heat, right? Or heat out, right? The exo being the out part, the thermic being the heat part. So generally when bonds are formed, when atoms come together and they form something new, they will give off energy. Heat or light goes out of that substance, and that's one of the ways we can tell when things are happening. If something gets warm, or if it gives off heat, or if it gives off light, that's how we can tell that stuff's going on. Okay? Because in the process of coming together, those things get to a lower energy state. As we've mentioned already, bonding deals with valence electrons, or electrons in the highest energy level. We've talked about the idea on several occasions that valence electrons are important to determining the behavior of an atom. Why? Because those are the electrons that are involved with bonding. When we talk about valence electrons, right, electrons in the highest energy level, generally, what does that mean about where they're located in an atom? Where are valence electrons in an atom?
On the outside.
Outside, right? Generally far away from the nucleus, or as far away as will exist for that atom. Okay? Good there. Okay. Because bonding deals with valence electrons, we have to have a way to focus just on the valence electrons of an atom, because that's really all we're worried about from a bonding standpoint. So to help us with that, we draw something that's called a Lewis structure. A Lewis structure is a symbolic representation of an element that shows valence electrons. Symbolic representation of an element that shows valence electrons. Yes, Andrew, go ahead.
Who was Lewis?
Lewis, I forget Lewis's real name, or real name, sorry. Lewis's first name, I forget his first name. He was a chemist back, like around the time, a little bit after Dalton. Okay.
But
so
before the Russian guy? So
no,
he's-
after
oh.
Mendeleev. Yeah,
So
we're
shortly
talking
after
more.
Mendeleev.
We're talking more like early 1900s,
Oh, okay.
something like that. So okay. All right. A Lewis structure consists of two parts. It consists of an elemental symbol and the valence electrons. And those valence electrons are represented by dots. So let's take a look at some Lewis structures. So the first Lewis structure that I ask you to draw, right, is lithium. Okay? So first thing we have to do is we have to find lithium on our periodic table. So you go to your periodic table, and you find lithium, and you find out that lithium's atomic number is what? 3. And that means that it has 3 electrons, right? So, if we were to write an electron configuration for lithium, it would look like this. Right? Does that look familiar?
Yes.
Now, do we want all of those electrons? Are we concerned with all of those electrons? No, just the valence electrons, right? How many valence electrons does lithium have? Just 1. Somebody explain to me how we know that lithium has 1 valence electron from this electron configuration. Andrew, go ahead.
Because because the
You want to spell
yeah, I just don't know how to explain
Okay.
it. It's the S1 because
Okay.
it's the farthest right.
it? Yeah. Let's go a little more. Okay, go ahead. What were you going to say?
Well, I was gonna say it's an alkali metal.
Okay, that's more of a pattern that we'll get. If we look at this electron configuration specifically, right?
Oh,
Christine,
is it like?
go ahead. Christine, go ahead.
Because the 2s is like the farthest ring out.
Okay. What's the highest energy level here in lithium?
2s.
Well, it's not 2s, it's,
S.
no,
2.
2,
Two.
right? 2 is the highest energy level, right? The highest principal energy level. And then, how many electrons are in that second level? Just 1. So, lithium's Lewis structure, we're going to draw Li to represent the symbol, and then 1 dot. Okay? Good there. Katarina, go ahead.
Does it matter what side you
No,
put it on?
absolutely not. And we'll talk about that a little bit more with oxygen here in a second. Okay? So the next one that I have written there on your sheet is oxygen. So we find oxygen on the periodic table. Right? What's oxygen's atomic number? 8. So that means that it has 8 electrons. Now, you don't have to write this, okay? But oxygen's electron configuration looks like this. Okay? What is the highest energy level for oxygen? Adrian, go ahead.
Sorry about that.
Okay.
To be full.
Okay. That's not the highest energy level. Julian. 2 is the highest energy level. Okay? Remember that energy levels have different parts within
Oh.
them, orbitals, right? So 2 is the highest energy
Oh, I
level.
was looking at. I was looking
Yeah, we can't just look at the end. We have to look at the whole level. Okay? So, hold on a second. So, how many electrons are there in the second level?
6.
6. Some are in the s orbital, and some are in p orbitals, but there are 6 electrons in the second level. Does that make sense? Okay? Now, watch me. Okay? You don't have to do it this way, but once we start, so Katerina, once we start putting in like these electrons, right? Think of it kind of like a box around the symbol, okay? 1, 2, 3, 4. Okay? Now, this idea we've kind of introduced before, right? Where does this idea come from? Do we remember this idea? What are these electrons doing here as I fill them in like this? They're repelling each other, yeah. What else did we kind of say about how they fill orbitals? Do we remember that idea? Andrew, go ahead.
It looks like the Bohr model a little bit.
Kind of like a Bohr model, a little bit. That's not what I was going for, but we talked about something called, or what were you going to say?
Never mind.
We talked about something called Hund's rule. Do we remember Hund's rule?
They go from like high energy to low energy.
Higher energy, lower energy. That's more Aufbau principle, okay? Hund's rule says how do they fill up, Dunphy?
They go into an empty one before going into one with other electrons.
They go into an empty orbital before they fill up orbitals, right? So here, when we start filling them in, we can start drawing them like this, where they're spreading out nice and evenly. Now, is this enough valence electrons, though? We said how many did there have to be? 6, right? This is only 4. So now we can start pairing them up, okay? If you draw it like this, okay, that's not wrong. Still has 6 valence electrons, right? But this is a little bit more representative of how it happens in nature, okay? So Katerina, that's like, does it matter? No, it really doesn't. And especially like on this one, it doesn't matter which one you have 2s and which one you have 1s. That doesn't really matter. But we try to make it this way to represent a little bit more about how it's like in the real world, okay? All right, does that make sense? Next one that I have on your sheet is fluorine. Is that right?
Yeah.
Okay, so fluorine, okay, you find fluorine on your periodic table, you find out that it has an atomic number of 9, so 1s2, 2s2, 2p5. How many valence electrons does fluorine have? 7, okay? The second energy level is the highest energy level. How many electrons? 7. Okay, Kevin, go ahead.
So to figure out how many valence electrons there are, you have to write out the configuration.
No, I'll show you how to do it shorthand in just a second. Okay, I'm just doing this to make a point to begin with, and then I'll tell you how to do it shorthand. Okay, so then when we start filling them in, right? 1, 2, 3, 4, 5, 6, 7. Okay, good there. Next one on your list is chlorine. Okay, chlorine, find it on the periodic table. What's its atomic number? 17. So its electron configuration, 1s2, 2s2, 2p6, 3s2, 3p5. Okay? That's chlorine's electron configuration. What's the highest energy level that is occupied with chlorine? 3. Jillian, how many electrons in that third energy level? 7. So even though chlorine has more total electrons than fluorine, what do we see about the number of valence electrons?
They still have the same energy.
Let's not go with
Same
energy.
number.
They have the same number of valence electrons, right? So their Lewis structures look almost exactly the same. Just the symbol is different. Okay? Good there? Then, last one, right? On your sheet there is neon. Okay? Let's not go there. Let's go purple. Just use a different color. So neon, right? Just to make our point, 1s2, 2s2, 2p6, right? So how many valence electrons for neon? 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Good there. All right. So, Catherine, go back to that question, all right? We've talked about the idea that when we look at elements in the same family, what do we know about elements in the same family?
Same amount of valence electrons.
They have the same amount of valence electrons, and that leads them then, Dunphy, to have the same kind of what?
What's the electron configuration?
Yes, I was going for something different. What do we know about elements in the same family? How do they behave? What kind of reactions do they do? They do similar reactions because they have the same number of valence electrons, right? So, if we look here, we did fluorine and chlorine, right? What did we see about the number of valence electrons that chlorine and fluorine both have? Well, yeah, how many specifically? 7, right? So if you did a Lewis structure for bromine, how many valence electrons do you think it would have? 7, right? So, Catherine, anything in this column is going to have 7 valence electrons, okay? We also did oxygen, right? What did we see about the number of valence electrons that oxygen has? 6, right? So, if I had to draw a Lewis structure for sulfur, how many valence electrons do you think it would have? 6. Anything in this column has 6, okay? We just did neon. How many valence electrons did neon have? 8. So anything in this column is going to have 8 valence electrons. Okay? The very first one we did, right, was lithium. How many valence electrons did lithium have? 1. Anything in this column has 1 valence electron. Yes, Jay?
Even helium would have 8 valence electrons?
No. So we'll talk about that there are some exceptions to that rule, all right? But as far as the pattern goes, okay, anything in this column has 1 valence electron. Anything in this column, 2 valence electrons. For now, we're going to forget about this section, okay? Let's skip that part, okay? And then we'll pick it up here. 3, 4, 5, 6, 7, 8. So Catherine, we don't have to write out an electron configuration every single time. If we know what column it's in, we automatically know how many valence electrons it has. They might be a different level, right? Fluorine's valence electrons are in the second level, chlorine's are in the third level, but it's still 7, okay? So you don't have to write out an electron configuration every single time. Okay? Nora, go ahead.
So would that mean that group 16 would have this like similar reactions as group 6?
No, because, that was a good question. Nora asked, does that mean that group 16 would have similar reactions to group 6? And the answer to that question is no, because once we start getting into these elements here, our transition elements, the pattern of filling isn't the same, because now we're dealing with d orbitals and not just s and p, okay? So Nora, for this section here, we're going to just sort of conveniently forget about this whole section right. Whoa, not a square. I don't want a square. Oh my goodness gracious. Let's go rectangle. There we go. Right. This whole section right here. All right. Let's for now, at least for this little section right here, let's just sort of forget about those. Okay. Okay. So let's just pretend they don't exist for now. Okay. When you take chemistry either next year or junior year, then you'll talk more about that. But for our purposes right now, we're going to stick just with these 8 columns. Okay. Andrew, go ahead.
I don't think you can pick, but those two backgrounds are so distracting on top of it. It looks like the blue thing has like shark fins and it's the ocean.
Try to focus, man. Come on. Try to focus. You can get past it.
I know. I was just trying to pronounce something stupid.
Is that better?
Yeah.
All right. Why is that
Oh wait,
important?
hey, what about the bottom one? Are you to talk about that as well?
What button?
Oh, the
What I forgot. What do you call that again?
No. Now we're talking about f orbitals, and we don't want to go there. All right.
Are you gonna block that out too?
What?
Are you gonna block out that?
Do you want me to?
If you want to.
No, you tell me. Do you want me to?
I don't care.
Because
Because
I can forget about it. I mean, I.
yeah, it was just a shock thing now. It's
Okay.
just-
All right. It's, okay. Why is that important? So we've talked about the idea that valence electrons are important because they determine chemical reactions. Why are they chemical reactions? Because valence electrons determine chemical properties of an atom. Okay? And the reason why that valence electrons determine the chemical properties is atoms are trying to get to 8 valence electrons. 8 valence electrons, and they will take the shortest route to get there. We call this idea the octet rule. Back when we introduced what an atom was and the different parts of an atom, what did we say about the number of protons and the number of electrons that an atom has? They are the same. Just because it's the same number of pluses and minuses, that doesn't mean, from an energy standpoint, that that atom is stable. Being equal does not mean stable. Okay? We will wrap it up for now, and we will pick this up tomorrow. Oh, wait. Sorry. Hold on. Freeze. Nah, never mind. I'll pick up from there.